what do you guys think? So what are the limitations of abstraction functions that you guys were thinking about? Anyone want to volunteer? I'll pick on some people. Yeah.
Yeah. So we were talking. We basically said that with abstraction functions, you can't really keep track of the past and you can't really see into the future. Those are kind of the two main problems of just doing an abstraction function. And so the reading goes into basically gives some examples of why you would need to care about the past and why it'd be helpful to know about the future. And yeah, it basically goes into how you can use this idea of these history variables in your implementation that will take care of the states that you've been in. And then you could also add something called a prophecy variable to kind of give a little insight into what states you might be in the future that allow you to relate more easily to the spec.
Yeah, I think that's basically right. Indeed, I think what the handout talks about is the history variables, prophecy variables. I think there's even a completeness proof that Butler will correct me if I'm wrong, that I think any specification can be proven with history variables and prophecy variables, as long as it's correct. And the other thing, I think, Kevin, did you want to say something?
Oh, sorry, I forgot I was.
Oh, no worries. Yeah. Anyone else?
Yeah, so I guess I was just going to add, I think we'd also talked about the point that if what you ultimately want to do is reason about equivalences between traces of the implementation and the spec, then the point is, I guess, history and prophecy variables will let you do that. So if you could write down a proof in terms of traces, then there's some way of writing down history and prophecy variables that will allow you to do it at the level of individual states, basically. So at the sort of most extreme, I guess, you could say, your history variable could literally have the contents of every single state that you've ever seen before, and your prophecy could have all the states you're going to see, and any reason you could do it at the level of traces, you could do that way. Of course, you don't actually want to make those your history variables, I guess, in practice. But I guess that's sort of like the completeness thing you were just talking about, I think.
Yes, I think that's probably a good intuition for why indeed this approach is correct, because you could effectively use these history and prophecy variables to model your entire trace, and then it's a safety property of trace inclusion of external visible actions, and sort of boils down to that. I don't think this literally sort of works out in that way, but still. And then there's this also, the handouts talk a little bit also about these abstraction relations and how they sort of come into the picture. And abstraction relations are kind of a strange thing. We use them actually quite extensively in the labs, partly because they're easy to set up in a logical framework like Coq. Turns out they, I think, are equivalent to history variables, but prophecy variables are funny in a way that abstraction relations don't capture, and you really need to explicitly model prophecy variables. Luckily, I think, as Butler will talk about, they are relatively rare in practical specs. Anyone else? So I think indeed the questions we asked for this paper is a little bit more perhaps mechanical and has a clear-cut answer than some of the other discussion questions we typically ask about papers. So I think, yeah, here the answer is pretty clear. History variables plus prophecy variables are pretty useful for dealing with situations where there's not enough state in the spec, and abstraction relations are another way to get there for history. Any other thoughts or comments before we jump into the lecture? All right.
Okay, we're all set.
Sure.
Let's get this going. There we go. All right. I have a new setup for writing on the screen. We'll see how well it works. It might be a little bit fragile. So today's agenda is we're going to try to understand more deeply this notion of code implementing a spec in terms of the traces of the code being a subset of the traces of the spec. And we're going to do some examples.
Hey, Butler, did you mean to share your screen with the slides that you have?
Didn't I do that?
I think
Oh,
it
sorry.
somehow disappeared.
Share screen. Oh, sorry. I didn't realize it's not enough to just, I always forget that it's not enough to just push on the screen, the thing you want to share. You have to also push the share button. Sorry about that. And then we're going to see the cases in which you can't cook up a suitable abstraction function without hacking things up in some other way. And the most common such other ways to need to add history variables or possibly abstraction relations. And the fortunately much less common because much more inscrutable way is to have to add prophecy variables. So we're going to see examples that illustrate all these points as we go along. This is fairly basic foundational stuff, certainly for the labs and also for a lot of the reading material in the course. So if there are things that are not clear, you should speak up right away. Okay. So the basic notion that we start with is this notion of what does it mean for a code to be correct? And the definition we've given is that the external traces of the code have to be a subset of the external traces of the spec. So the way you're supposed to think, you should think about this is the spec describes what the allowed behaviors are, and the code has to conform to that. The code doesn't have to display all of the behaviors that are allowed by the spec, but it does have to be the case that any behavior that the code does display is a behavior that the spec allows. And sort of the whole point of this is that it throws away a lot of information because we're only talking about external traces. And we'll see what that means concretely when we look at some of the examples today. But if you go back to the file system example that I had a couple of weeks ago, the spec says that a file is just a sequence of bytes. But the code, of course, says that a file is represented by a bunch of disk blocks that are being pointed to by the index information in the inode. You don't see anything about that in the spec, and therefore you don't see anything about it in the external code traces. What does that mean? What that means is that when you invoke operations on the file system like read and write, you don't see anything about inodes, you don't see anything about index blocks, you don't see anything about the disk. All you see is those bytes. So lots and lots of information is being thrown away, which is exactly the point, because the whole purpose of specs is to simplify things and concentrate your attention on the things that are essential for what it is that you're trying to do. So a couple weeks ago, we also talked about, and I guess since then too, we've talked about the fact that specs can say two different kinds of things, safety and liveness. So safety tells you what the code may do, or to put it another way, it tells you that the code should never do anything that is recognizably bad. Liveness, on the other hand, tells you what the code must do. That is, eventually it has to do something good. So we can perhaps make this clearer by tying it back to a much simpler situation than the concurrent and crash-ridden examples that we spend most of the course on. Think about what these two notions mean in the context of a sequential procedure. So here's a concrete example of a sequential procedure. It's sort. You feed sort an array and it gives you back a sorted array. The spec for such a procedure is a relation between initial and final states. In the case of sort, what is the relation? The relation is you feed in an arbitrary array and you get back a sorted version of it, i.e. you get back something that's a permutation of the input and has the property, that, whoops, forgot to turn my writing on, has the property that Yikes! What did it do? Has the property that a sub I is less than or equal to a sub I plus 1 for all I in the domain. I won't bother to write that. So the specialization of this definition of equivalent traces to the sequential case. In the sequential case, the trace only has two elements, the initial state and the final state. The trace of the spec only has two elements, the initial state and the final state. And the correctness condition is the relation that the code establishes has to be a subset of the relation that the spec establishes. In this example, you might think that the code relation is the same as the spec relation. But of course, that's not actually true, because this specification, which just says that a sub I has to be less than or equal to a sub I plus 1, if the comparison operation between the array elements is only looking, suppose the array elements are records. So suppose that one of these A's is a record consisting of some I field, or let's call it J, some J field, and then some other stuff, and we're just sorting on the J field, then the only thing this spec says is that the J fields have to be increasing in the output, but it doesn't say anything about what happens when two guys are equal, have equal J fields. So the spec says any of those cases where any of the ordering of elements that have equal J fields are going to be acceptable. The code most likely is going to be deterministic and is only going to produce one of those. So in that case, the code relation is indeed going to be a proper subset of the spec relation. Now, in this simple-minded sequential situation, safety simply means that the spec allows the final state of the code. So in our sorting example, the code state, the final state of the code has to be a sorted state. The spec allows any sorted state where the J fields are non-decreasing. And that's called partial correctness. What that says is if the code terminates, then it's going to satisfy the spec. In this simple sequential situation, liveness corresponds to termination, which means that it actually does terminate. So you can see that this is a special case of the more general ideas of safety and liveness. Safety says that if you do get an answer, it's going to be correct. You're never going to get an answer that's wrong. Liveness says that you are eventually going to get an answer. So this is the fundamental story about the correctness of code. Does the code satisfy the spec? Are the code traces a subset of the spec traces? And as we go along, we'll see lots of variations on this basic idea.
I have a question, Professor.
Yes.
I'm just a little bit unclear on like what exactly constitutes an external versus internal trace.
Well, informally, the external trace is the things that the client can actually see. So in the sorting example, for instance, there's the initial state, which is the input array, and there's the final state, which is the output array. Those are the things that are visible. Oops, sorry, I'm getting a message here. Your session is going to spawn. Oh, sorry, that's irrelevant. Never mind. Sorry, where was I?
Internal versus external.
Right. Internally, the code for sorting is going to perhaps generate some auxiliary data structures. Suppose it's quicksort, then you're going to have internal variables that keep track of where you are in the partitioning process that quicksort implements. But none of those things are going to show up in the spec. None of those things are going to be external. We will see in a couple of slides an example of a spec that has internal state as well. but there's a concrete example of the code having internal state. And we're going to see a bunch more such examples as we go along. So why don't you hold your question and ask it again in about half an hour if it hasn't already been answered, okay?
Sounds good.
So the basic idea for simulation, for proving that the code satisfies the spec, is this idea of simulation, which is that the code matches the spec one action at a time, and then you string those actions together to get the general case. Okay, so let's do a simple example. This is an example where I hope that the basic ideas will already be very familiar to you from other work. And the example we're going to do is use this code for memory that has a cache. So the spec for the memory says a memory is a function from addresses to values, also often called a key value store in a context that's more general than just the hardware memory. And the state of the memory spec just has a single variable m, which is a memory. That shouldn't be any big surprise. And it has two interesting operations, read and write. Here they are. It also has an initialization operation, which says choose some arbitrary memory which has the property of that its domain is the addresses, and then it sets that to be the value of the memory variable. So that says memory gets initialized in some arbitrary way, but it has to be defined on all the addresses. Read just says give me back the A value of the memory. Write says change the A value to be V. That should not be any big surprise. Now let's look at the code for implementing this using a write-back cache. So here we're going to introduce another type, which is very similar to the memory, but instead of A to V, it's A to option V. I've abbreviated option as OPT so that it doesn't take up so much space on the slide. So what this says is that the cache is only defined on some of the addresses. And in fact, our cache is going to be defined on exactly 4,096 addresses. And now we have two variables in the code. One of them is the memory that the code maintains, and the other is the cache itself. And we're calling those MC for memory in code and C for cache. And now the read and write operations, this initialization is not very interesting. It just says make the cache be of size, C size, make it so that it's defined on exactly C size variables, because what this says is the domain of the cache is the set of addresses on which it is defined, i.e. where the value is not none. And the size of that is going to just be C size. And we wanted to agree with the memory on all the places where it is defined. But then the read and write operations now are going to do what they do on the cache. So we're going to return the cache at A, and we're going to set the cache at A to be V. But before we do that, we need to make sure that A is actually in the cache, and that's what this internal load action is going to do. Okay, so let's revisit the question of internal versus external here. The external state is just the results of the inputs and outputs of the read and write actions, which are the only two external actions in this spec. The internal state is the code's memory and the code's cache. And we'll see that these external operations of the code have to agree with the external operations of the spec. Otherwise, there's no hope for getting the traces to agree. The internal action here is load, and it doesn't correspond to anything in the spec. Normally, the code has lots of internal actions. In the extreme case where the code is actually machine code, the internal actions are going to be the execution of the individual machine instructions, and there may be millions or billions or trillions of those corresponding to a single external action. Okay, so here we are in the internal actions for the cache. Here are the external ones, just to remind you. The internal action that we saw here is load, and what load says is if the cache is already defined at A, then you don't have to do anything. But if it isn't, make some space by flushing one entry from the cache, and then set C at A to be MC at A. So after we've done the flush, the cache is only defined at C size -1 locations, because what flush does is to free up one location. And then after we set C of A to MC of A, the cache is defined at C size locations again. And what does flush do? It says pick an A in the domain of the cache function. If the cache matches the memory at that location, then we don't have to do anything. But if it doesn't, then we have to update the memory from the cache. Because remember, when we do the write, we only write into the cache. We don't write into the memory. But now we're going to bounce this A entry from the cache. And so we better make sure that we don't lose the value. So in order to make sure we don't lose it, we write it back here into the memory. And then we make the cache undefined at A. So flush 1 frees up one slot in the cache by bouncing one of the addresses that's in there. And then when load uses that up again immediately. Note that this is an interesting example of a case where the spec for read and write is perfectly deterministic, but the code is not deterministic because it gets to choose which cache value to flush. So what's the abstraction function here? The job of the abstraction function is to take the code state, which is M, MC, C, to the spec state. And how is it going to do that? The spec state is going to be just the code state, the code memory overlaid with the cache. So what is this idea of function overlay? The idea of function overlay is if the function's defined, if the argument A is defined at C, then the answer is C of A. And if it isn't, then the answer is MC of A. So here this is written out. M is going to be, this is another way of writing the abstraction function without using this function overlay notion explicitly. The memory is going to be a function from A to, which produces, if C of A is different from none, then C of A, otherwise MC of A. Okay? So why does the abstraction function go from the code to the spec? The answer is the code has many ways to represent the spec. And so it wouldn't be feasible to have the function go from the spec to the code. Another way of thinking about it is what Nikolai was saying a few minutes ago. The job of the abstraction function is to tell you how it is that the code is representing the spec. And the obvious way to do that is to give you a function from the code state to the spec state. This, however, as we'll see in the next example, this is an oversimplification. Sometimes the spec is better off with more state, and then we need a history variable in order to generate the abstraction function. So the ground rules for abstraction function, you have to satisfy two conditions. The first one is kind of boring. If T is an initial state of the code, then F of T is an initial state of the spec. The interesting one is the simulation condition, which says, oops, if T is a reachable state of the code, and there's a step of the code from T to T prime, then there has to be a step from F of T to F of T prime that has the same external visibility, i.e. pi in this notation. So it has to have the same, the pi has to be the same here in the spec as it is over here in the code. So let's look at that with a picture. I've just written down the same thing that I went over on the previous slide. This is a copy of it here. And here's the picture. You're going to go, if you can go from T to T prime, then there has to be a corresponding way to go from F of T to F of T prime in the spec, such that the abstraction function takes you from t to f of t, and it also takes you from t prime to f of t prime. So what this says is, and we like to say that this diagram commutes, which means that if you go around it this way, you get the same answer as if you go around it this way. So what this shows is that the trace, that one step of the code is allowed by one step of the spec. And in fact, we know exactly which step of the spec it is. It's the step of the spec that goes from f of t to f of t prime, where f is the abstraction function. And therefore, the theorem tells us that if there is such an abstraction function f, which takes us from the t state to the s state, then t implements s. That is, every trace of t is a trace of s, which is what we mean by implements. Why is this true? It's true because of induction. How do you prove this? You prove this by induction on the length of the trace. You start with an initial state that corresponds, and then as the code evolves from state to state, the spec has to correspondingly evolve from state to state, because at every step we can apply the abstraction function, and we can see that the external behavior is the same. Okay, that's the basic idea. Now there's one very important wrinkle on this idea that doesn't show up directly in this picture, which is t has to be a reachable state of the code, and not all states of the code are reachable. So for example, suppose we have code that maintains a table, a sorted table, and does binary search on that sorted table. So suppose we're going to have a sorted table A. And our idea is we're going to do binary search on this table in order to look up some value. If we describe the state this way, then there's nothing in this state description that forces the array to be sorted. But if the array isn't sorted, the lookup isn't going to work. So there has to be, the invariant has to say, sorry, a reachable state has to be one where the array is sorted. And that's what the invariant is going to say. And it's not going to be true that a step of the code corresponds to a step of the spec if the array isn't sorted, because the binary search isn't going to work. So that's the job of the invariant. It's to characterize the reachable states. And we only need to show that the code simulates the spec from a reachable state. The invariant doesn't have to perfectly describe the reachable states, but it has to bound them well enough that we can make the abstraction function story, that we can find an abstraction function. And as the sorted array example tells us, the code doesn't simulate the spec from every state, but that's okay. It only has to simulate the spec from reachable states. So how do we prove that something is an invariant? Usually we do that by induction on the length of executions, i.e. typical induction, P is true initially, and then if P is true in state S, and S goes to S prime, then P has to be true in S prime. That's how you prove these invariants. It's very similar in style to the way in which you prove the simulation itself. So let's look at some other examples of invariants. In the write-back cache example that we just saw, the only invariant is the size of the cache. And the invariant is that the size of the domain of the cache has to be C size. And we maintain that because the internal flush run action shrinks it by 1, and then the load action kicks it back up by 1, so the cache size doesn't change. If we had different code that was using a hash table to implement the memory spec, then there'd be a more interesting invariant. It would tell us that if the value v is in the bucket that has hash h, then the hash of v better be equal to h. because otherwise, of course, when we do the lookup, we won't find it. And let's look at another example. If the cache entries have dirty bits, then the invariant is going to say that if the cache is different from the memory, then the cache entry had better be dirty. So let's look at that in a little bit more detail. If we want to add a dirty bit, here we are. We used I've put in red the added stuff for dirty bits. So now a cache entry is going to have two fields, the value that it had before and the dirty bit, which is just a Boolean. And the dirty bits are going to start out false. And when we do a read, we're just going to give back the value, no big surprise. When we do a write, we're going to set the dirty bit to true. So far, we haven't done anything with the dirty bits. We've just kept track of them. But of course, the load operation, the flush operation is going to pay attention to the dirty bit. So remember the flush operation, it picks some address in the cache to flush. And then now it's going to say if the cache, what it said before was, if the cache entry is different from the memory, then we better write it back to the memory. That's not very attractive in the implementation because it means that whenever we do a flush, we have to read the memory to find this out. So that's the motivation for dirty bits, is that the cache can find out whether it needs to write back to the memory without having to look at the memory. So if the dirty bit is true, then we write back. Otherwise, we don't do anything. And the rest of it is the same as before. Okay? So here's the amazing thing about the abstraction function method. If it's true that the code implements the spec, sorry about that. If it's true that the code implements the spec, remember what that means is T is a subset. The traces of T are a subset of the traces of S. If it's true, then the simple abstraction function method will always work, provided the spec avoids having extra state, more state than you can map from the code. The spec avoids having too few or too many transitions, and the spec avoids premature choices. Well, typically, it's not true that the spec and the code have the same number of transitions. In fact, we saw that in the previous example, where the spec only has read and write as transitions, but the code also has load and flush. Extra state, we didn't see that in the previous example, but we're going to see it soon. And premature choices, that's much more unusual. We'll be talking about that towards the end. So looking at what it says at the top of this slide, you might say, why bother? All we need to do is make sure that the spec avoids these mistakes. And we can use the simple abstraction mechanism. We don't have to fuss around. But there's a fundamental flaw in that way of thinking about things. And the flaw is that it misunderstands the purpose of the spec. The purpose of the spec is not to make it easy to prove that the code matches the spec. If that's all we wanted, we could use the code as the spec, and that would be the end of it. And of course, people often do that. The purpose of the spec is to be as clear as possible to the clients and to disclose as little as possible about the internals of the code that's not relevant to what the clients need to know. It's not the purpose of the spec to make it easy to do the proof. But of course, you have to expect to pay for this somewhere, and these are exactly the places where you're going to have to pay. Okay, so let's look at the example of extra spec state. And this is an example that we're going to work out, that you are going to be working out in detail in the labs. So a tiny bit of notation. If Q is a sequence of T's and circle plus is an operator on T's, then fold of plus over Q means Q is 0 to circle plus Q1 up to Qn. And of course, that works for sets too. And you're probably quite familiar with this notion of folding an operator over a sequence or a set. So the sum of all the elements of Q is just going to be folding plus over Q. So here's the idea of this spec. We're going to have a statistical database which computes means and variances. These are the definitions copied out of a textbook for the mean and the variance. And here's the spec. It says this the state is a single variable dB, which is a sequence of values. Starts out empty, and the operations are you can find out, you can add a value to the accumulated collection of values, and the spec just adds that to the dB sequence. You can find out how many guys have been added, dB.size, and you can find the mean and the variance. And how is the mean defined? Well, if dB is empty, then the mean is undefined. Otherwise, it's the sum of dB divided by dB.size. And similarly for the variance. This is about the most straightforward spec you can imagine writing after reading the textbook. Any questions about that? Okay, but of course, you wouldn't want to write the code this way, because the code, if you wrote the code this way, you'd be building up this bigger and bigger sequence of values, which isn't actually needed in order to do the job that the spec says you have to do, which is to be able to tell how many guys have been added and what their mean and variance is. So here's the efficient code. Instead of having the dB as state, you have three integers: count, sum, and sum of squares. And what add does is it increments count by 1. It adds v to the sum, and it adds v squared to the sum of squares. And now how do we compute the mean? Well, if the count is 0, it's undefined. Otherwise, it's the sum divided by the count. Big surprise. And similarly for the variance. So that's the efficient code for this statistical database. And it's unboundedly more efficient than the code that you would get if you just used the spec, because that code is going to use more and more state as you add more and more values, whereas this code always uses a constant amount of state, namely just these three integers. But the problem is there's not going to be any abstraction function from this code to the state, to the spec, from the state of this code to the spec. Why? Because the spec has more state than the code. The spec has this dB thingy, and there's no way we can conjure up all of that dB from the three nats that are the only state we have available in the code here. So one's first reaction might be, this is a bad spec, but it should be clear from this example that that's wrong. The spec is the most straightforward way of expressing what it says in the textbook. And presumably, statisticians worked for a long time to figure out that these are the right definitions. These are the things you should actually care about. Again, the job of the spec is to be clear, not to be efficient. So how are we going to get around this? Well, the answer is we're going to have to add history variables to the code in order to track the extra spec state. In this case, it's especially simple. We just add the whole dB thing, the entire state of the spec, and then we also have to add the spec's action. dB gets dB plus v in the add operation of the code. This trick of adding all the spec state will always work, but often you don't need to add as much. You can just add a couple of things in order to get enough state in the code to be able to find an abstraction function. Now, the ground rules for the history variables are that they're not allowed to affect the ordinary variables. So it should be obvious that the code with history variables has the same traces, because the history variables are just kind of monkeying around on the side. They're not messing around with the actual traces that the code can generate. So now, what we were shooting for was code is a subset of spec, and what we actually have is code is equal to code plus history, because the history variables are not changing the traces. And code plus history is going to be a subset of spec, because the abstraction function is going to work for this case. In order to make it work, we need an invariant that relates the dB in the code to the rest of the state. And what is that invariant going to be? Well, it shouldn't be any big surprise. It's going to say that count is the size of dB, sum is the fold of plus over dB, and sum of squared is the fold of plus over dB composed with square. And why do we need this invariant? We need it because we need to show that the value that the code's mean returns is the same value that the spec's mean would return. And what the spec's mean returns is the sum of dB divided by dB.size, and what the code's mean returns is sum divided by count. So those had better be equal. And that's exactly what this invariant says. And I hope it's reasonably clear that proving that that's an invariant from this code is not going to be difficult. Okay, so that's one way to do things, is to add a history variable to deal with the possibility that the spec state has more stuff in it than the code state does. Another way is to generalize the idea of an abstraction function to an abstraction relation. So that that generalization is meant to be suggested by this picture. At the bottom of the picture, we have the code state going from, hello? What's happened? Dear me. It's not happy. Let's try again. Well, maybe we'll do without writing for a bit. I don't know what's gone wrong. The code is going from t to t prime, just as it did before. And here we have the spec going from S2 to S2 prime, just the way we did before. But now we're not going to have a function, we're going to have a relation, which means that there could be more than one spec state corresponding to a single code state. In this picture here, I've shown two spec states. So in addition to S2 going to S2 prime, another possibility is that the abstraction relation relates T to S1, in which case S1 had better go to an S1 prime, so that T prime relates, the abstraction relation relates T prime to S1 prime as well. And of course, there could be lots and lots of these guys. So the way to think about this, so reset. So stating the simulation requirement more precisely, if T and S are both reachable and T is related to S by the abstraction relation, and there's a T step called pi, then there has to exist an S prime such that pi takes S to S prime by an S step, and S prime has to be related to T prime. So remember, when we had the abstraction function, we just said that we would map T to F of T. Here, there could be lots of different S's that T is related to. And for each one of them, there has to be a pi step that takes you to an S prime, so that T is related to S prime. So this is a strong enough next step that you can still make the induction work. And the way to think about it is, T and S are running along in parallel. T is doing the execution since it's the code, and so T is doing whatever its code says it wants to do. And S is following along, and it's producing the same external trace. And these two conditions, initial and next, guarantee that S can always produce the same external trace. In the same way that previously with the abstraction function, it was perhaps a little bit more obvious that S would always produce the same external trace. Okay, now would be a good time to ask questions about abstraction functions and abstraction relations if it isn't clear. Because this is really essential. If you're confused, if you get confused about this, you're going to have a lot of trouble. Okay, and here's the abstraction relation for StatDB. Again, it shouldn't be any big surprise. In fact, it's exactly the same as the invariant that we had for the history variables. But here the dB, of course, is in this. When we had the invariant, the dB was the dB history variable that we added to the code, whereas now the dB is the dB of the spec. But it's doing exactly the same thing. It's telling us how count, sum, and sum square are tracking dB. Okay, so that was a little bit tricky, perhaps, especially the abstraction relation version of it. The next thing is really pretty simple. Now we want to allow for the possibility that the spec and the code take different numbers of steps. And yeah, we're going to just look at one concrete example where the spec is taking more steps than the code, because that is perhaps a little bit less familiar. If you remember the drop action from the async messaging spec, though, you'll see that that's an example of how there can be an internal transition in the spec that doesn't correspond to any transition necessarily in the code. And we're actually going to see that in a little bit more detail in another couple of slides. So the idea here is, if T and S are reachable states as before, and T is related to S, and pi is a step from T to T prime, then we're going to relax the previous requirement that there be a single step from S to S prime. And we're going to say instead of that, there has to be a sequence of steps from S to S prime that has the same trace. So what does that mean? It means that it has to have one pi step, because it has to match up with this pi. And it might take other internal steps which don't cause any change in the externally visible trace, or in the language of labels on the state transitions. All the transitions except the pi one are internal, and so they have a sort of a blank label. So here's a picture. You start in S0, you go through various states until you get up to Si, doing internal transitions which are not visible externally. Then you go from Si to Si plus 1 doing pi, and then you do more internal things until finally you get to S prime. So that's the requirement. It's not so common to have more spec transitions than code transitions. It's very common to have more code transitions than step transitions. For example, as I was mentioning a few minutes ago, if the code is actually machine code, then every machine instruction is going to be a code transition. So there's going to be lots of code steps for every spec step. Okay, so now we're done with history variables, and we're done with extra transitions in either the code, extra invisible internal transitions in either the code or the spec. Now we're going to get to a more exotic thing, which fortunately it's not very likely you're going to need. The reason for discussing this third thing is that it actually is possible that you might need it. I'm going to try to convince you of that by giving you two realistic examples. And secondly, because once we've added to the basic abstraction function story the history variables, the internal transitions, and the prophecy variables, now we have completeness. In other words, where does it say that here? No, it doesn't say it. I guess I had the completeness slide earlier. It's perhaps surprising, but it's true that with all these additions to the basic abstraction function story, the method is complete. What does that mean? That means if the code actually does implement the spec, then you will be able to find an abstraction function, possibly after adding history and prophecy variables, for which the diagram commutes. So this method is always going to work. The theorem doesn't tell you how to find the abstraction function, at least not in any useful way. But it does give you a guarantee that it exists. So do not despair. If you can't find an abstraction function, hopefully the struggle to do so will make it clear to you that you have a bug in the code, or possibly a bug in the spec. So let's look at a couple of examples where you actually need the prophecy variables. Here's a reliable two-party channel spec, which we actually had on the screen a couple of weeks ago. There's a channel, which is a sequence of messages. You can send by appending a message to the channel, and you can receive by pulling a message off the head of the sequence. No big surprise. If there's a crash, you might drop some messages. So how do we model that? We say that well, what happens in a crash is that we pick some subset of all the messages in the channel, and we delete the. We just keep the ones that are in the subset, and we erase the rest. So here's a picture that shows how this composition actually does that. Here's the messages we're going to keep, which have been sorted now. So into a sequence, we're just going to keep messages 1 and 3. We're going to compose that with the original channel, which has maps 0, 1, 2, 3 to A, B, C, D. And the composition of these two guys maps 0, 1 to B and D. So it does exactly what you want. What was the point of that? Of course, I could have said this in other less concise ways. The point was, once you learn to use the language of sequences and composition and relations, you can say a lot of things very precisely and also very economically without adding a lot of additional internal machinery. So it's, in my view anyway, it's very much worthwhile to learn some of this language. The code for this reliable messaging is, think TCP, is going to use an underlying asynchronous messaging. So how does asynchronous messaging work? We saw this a couple weeks ago too. In asynchronous messaging, the channel is a set, not a sequence. And the send operation is going to just add the new message to the set. The receive operation is going to try to find a message in the channel and return it. And there's going to be an internal non-deterministic drop operation, which says if you can find a message in the channel, you can take it out. And that can happen anytime. So this is the abstraction of the internet's basic packet protocol, which shows up to clients as UDP, unreliable datagram protocol. So in real code for reliable messaging, such as TCP, this spec is it's not straightforward to understand why it is that this spec is true, because the spec says that if there's a crash of either the sender or the receiver, you're going to lose some subset of the messages. So why should that be true? In real code, the message can be lost long after a crash. Why? Because the code has sent a message. It's sitting there in the channel. It can stay in the channel for a long time. Once the code has crashed, if the message is dropped, if the asynchronous message is dropped, then the synchronous message gets dropped because there's no retransmission. If the sender doesn't crash, it doesn't matter whether the asynchronous message is dropped because the sender will retransmit enough times to get the message through. But in the case of a crash, if the asynchronous message is dropped, then that's the end of the message. It's not going to be delivered. On the other hand, if the asynchronous message is received, then the message is received. So this event of either receiving or dropping the message can happen long after the crash is finished, because things can live in the network for a long time. So what that tells us is that we're not going to be able to have a trace that has, think about the trace of the sender. The sender does send operations and occasionally crashes. And then the receiver does receive operations. There's not going to be it's not going to be possible to have a trace which respects an argument which respects the notion that messages can only be lost at the time of the crash, because we just saw that in the code, messages can be lost much later. So how could we fix this in the spec? We could make a somewhat messier spec, which says that a message, this is the spec now, remember, not the code. The messier spec says that every item in the channel is not just a message, but a pair consisting of a message and a mark. And the mark, the job of the mark is to tell you whether the message was in the channel being transmitted at the time of a crash. So when we send a message, the mark is going to be false. When we receive a message, it's the same as before. Nothing's changed, except we have to pull out the M component of this pair. Drop says if an MK has gotten to the head of the channel and it's marked, then we can toss it. We don't have to toss it, but we have the option to do that. And what crash now says is mark all the messages that are in the channel. So compose the channel with a function that maps the existing MKs to mk.m, true. So this spec now does not have the problem that the previous one had, because drops are now delayed until can be delayed until receive time, which is the latest you would care about it. So that's an example of a case where it's not going to help to add history variables. It's not going to help to add invisible internal actions. There's a fundamental difficulty caused by the fact that the original spec, which is here, is making a decision sooner than the code is making it. That's why it's called premature choice, because the spec is making the decision too soon. If you think about it, though, the spec with premature choice is equivalent to this spec without premature choice, because an external observer who can only see these send and receive actions taking place, and the crash too, but cannot see the drops. The external observer can't tell the difference between the first spec and the second spec. And the second spec will be able to prove correctness of the code without having to worry about premature choice, because the second spec doesn't have any premature choice. However, to prove that this spec that's on the screen is equivalent to the original spec with premature choice, you're going to either need a prophecy variable if you want to use the magic abstraction function method, or you're going to have to do it in some other way, which of course is not out of the question. In this case, I've kind of done it informal, just with willpower.
Wait,
So
I have a quick question.
Yes.
What exactly is the premature choice here? Is it the crash, or like?
Premature choice is the decision about who is being kept and who is being dropped at the time of the crash. This is the only opportunity that this spec gives you to drop things at the instant of the crash. Okay.
Okay.
Whereas this other spec gives you an opportunity to drop marked messages anytime.
Makes sense.
Which corresponds more closely to the way the code works, because the code is going to drop a message exactly when the message disappears from the asynchronous messaging channel. If a crash has to happen, so there's not any retransmission. Okay, let's look at another example, which is a little bit more subtle. This is the second of the three realistic examples that I know of where you might need prophecy variables. Where you do need prophecy variables. So this is consensus. You may have studied consensus under the name of Paxos when you studied if you studied distributed systems. This is the bread and butter of building a reliable distributed system out of unreliable components. So the idea of consensus is you're gonna get a bunch of parties to agree on a particular value. So here's the value. It's called agreed. And it starts out none and eventually gets changed to some value that everyone's agreeing on. So what does the spec say? The spec says you can allow some values. These are the values that it's going to be okay to agree on. They're the values that, in the typical application, these values are actually commands that you want to execute in a replicated system. For example, reads and writes of a replicated file system. We can't allow just, we're not interested in getting consensus on just any old thing. We want to get consensus on some read or write that somebody actually wants to do. So allow is the abstraction of that. And the way the spec handles allow is it says, you take the value and then you have a variable A, which is going to be either V or it's going to be none. And then if you haven't yet agreed on anything, then you can agree on A. And of course, if you chose A to be none, this isn't going to change anything. But if you chose A to be V, it is going to change something. You're going to now have agreement. So the decision gets made at the time that the value gets allowed. Another name for allow is propose, by the way. And then there's one more action called result, which says choose A to be either agreed or none and return it. So what this says is optionally you're going to return the agreed value. But even if you do have an agreed value, you might still return none. Why? Because in the intended, this is intended to model a situation where a bunch of machines are trying to agree on some value. And it's possible that a majority of them have actually agreed, but you're talking to one that's not in the majority, and so it doesn't know about it yet. In which case, it's going to return none, even though in fact there is an agreed value. So this is it seems a little weird that even after you've gotten agreement, you still might not find out about it, but it's an essential part of the fact that it's a distributed system. So this spec does premature choice. It chooses the value to agree on as soon as the value is allowed, because here it is choosing. Okay? Here's a somewhat more complicated spec. You can see it's about twice as big, which works much more the way the code does. Of course, what the code is going to do is you're going to, in the code, clients are going to walk up to one server or another and propose commands to be executed. And the code is going to remember those proposals, those allowed values. And the code processes are going to chat with each other to figure out which one is agreed on. So here, what allowed is going to do is it's just going to add V to the allowed set. And then there's going to be an internal action called agree, which is going to pick something out of the allowed set and set agreed to that value. Assuming we haven't already agreed on something. Once we've agreed, then we can't change our minds. And then results is going to be exactly the same as before. So this is the second example of where you have a simple spec that makes a premature choice. In this case, the premature choice is that as soon as you find out that a value is allowed, you decide whether to take it or not. And consensus without premature choice is going to defer that to some later time, namely the time at which you execute the internal agree action. This corresponds much more closely to what the code is actually going to do, because as I said, what the code is going to do is that all the processes are going to chat with each other to choose a value, and not until they've finished chatting are we going to know what value was agreed upon. So premature choice here, no premature choice here. In both of these cases, you're going to need a prophecy variable to make it work. And what the prophecy variable is pretty weird, and if you don't understand it, you shouldn't feel too bad, because I don't know anyone that really understands it. I know several people that can turn the crank of the machinery, but for everyone that I know, it's kind of you feel kind of strange while you're turning the crank, and you have to look very carefully at the formal rules in order to convince yourself that you're turning it correctly. So you don't have to feel too badly about it, because as I said, in 20 years of knowing about this stuff, I only have seen 3 realistic examples, and I've just shown you 2 of them. But here are the rules for prophecy variables, just for completeness. History variables, every initial state has to have a history variable value. Prophecy variables, every state has to have a value, because the intuition for prophecy variables is you're going to do the analysis of the transitions, working backwards from the end rather than forwards as you do intuitively. So for history variables, no existing step is allowed to be disabled by any new guards that involve H, because the basic idea with history variables is the H's are running along in parallel to the rest of the code, and they're not allowed to mess with what the rest of the code is doing. So they certainly can't disable any existing steps. Prophecy variables, no existing state, looking backward from the end is going to be disabled by what P does. So what does that mean? It means if there's a pi step from T to T prime, and T prime P prime is a state, then there has to be a P and a step of TP such that TP takes you to T prime P prime. So you can always reverse it when you're thinking about going backwards. This is the condition that causes all the conceptual difficulty. Condition 3, assigning to a vanilla variable doesn't depend on the history variable. The history variable live in their own separate space. And you have the same assignment rule for the prophecy variables. The prophecy variables can affect what actions are enabled according to condition 2, but they cannot affect how an action changes a vanilla variable. And finally, if T is an initial state and TP is a state of TP, it has to be an initial state as well. So those are the formal ground rules for prophecy variables, and you should never need them. What you should do instead, if you run into one of these premature choice situations, is you should deal with it at the highest possible level. And I demonstrated that in the examples. You should write another spec that's as high level as possible, but doesn't have premature choice. And then you should either use a prophecy variable or use sheer willpower to show that S prime is equal to S. And then from then on, the difficult task of proving that the low-level code actually implements the spec won't involve prophecy variables, because you'll be working with S prime rather than with S. Okay, that's the end of the story about abstraction functions, history variables, prophecy variables, and internal actions. Questions? Now's the time to ask. No, everything's crystal clear. That's very gratifying.
Wait, I have a question.
Yes.
So if you go all the way back to abstraction relations, right. So I think I just misunderstood this, but I think I'm still sort of stuck with the invariance with the history variables viewpoint. But should there not be a required sort of connection between S1, S2, and S1 prime and S2 prime in this situation, or is it just enough to say?
Yes, absolutely. They have to. You have to be able to get from S2 to S2 prime via pi.
I meant S1 to S2 and S1 prime to S2 prime.
No. See, here's the abstraction relation for StatDB.
Yeah.
All it says is that the code variables count, sum, and sum of squares have to have this correspondence with the spec variable db. But there are a lot of ways that you could have 2 different dbs that have the same count, sum, and sum of squares.
Okay.
Right.
Yeah.
For example, I could add 3 and then add 4, or I could add 4 and then add 3. That gives you 2 different dBs, but everything is, all these guys are going to be exactly the same.
Right.
So
Okay.
no, there's no, the only relationship between S1 and S2 is that they're both related to T by the abstraction function, by the abstraction relation. But they don't have to have any particular relationship to each other. Well,
Okay.
that's not quite true. The relationship they will have to each other is that they'll have the same count, sum, and sum squares, because that's what the abstraction relation says. That's what it means to be related to T. Many people, including me, find that a more comfortable way to think about this is in terms of the invariant that we had in the case of the history variable and abstraction function proof, which is exactly, this invariant is exactly the same. Two things about this invariant. Number one, you need it in order to make the abstraction proof go through once you've added the history variable. And number two, it's exactly the same as the abstraction relation.
Is there an example where the abstraction relation is different from the invariant for the history variable?
Probably, but I can't think of it offhand.
Okay.
Probably the reason that that would be the case is that this is an example where the entire state of the spec was turned into a history variable, and that doesn't always have to be true. In fact, usually you try to make the history variable as minimal as possible, because well, mumble. I'm not sure. I take that back. I'm not sure that that's true.
Wait, so the point of making the history variable as minimal as possible, is that because when you're trying to prove the correctness of the code, you want that sort of like extra history variable process to be as minimal as possible as well for performance reasons, or was?
Well, it wouldn't be for performance reasons, because remember, you don't execute any of the history.
Oh, okay, yeah, that's right.
No, it would be just because you want to mess with the code. My thought was, it would be because you want to mess with the code as little as possible. But it's probably not actually true, because if you make the history variable, if you choose the history variable so that it doesn't include all of the spec state, what that's probably going to do is my guess is that the invariant that relates, the combination of the invariant and the abstraction function are going to be the same thing as the abstraction relation. That's what's going to happen. And you maybe get to choose how to trade off between what goes in the invariant and what goes in the abstraction function in the case of the history variable. Whereas in the case of the abstraction relation, everything is in the abstraction relation.
Okay, I see. Thanks.
Other questions? Okay, I guess we're done then. You'll find the slides on Piazza in the resources section, in case you want to pore over them.